to review the definition of a limit, we can see that if f of x becomes arbitrarily close to unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L. All that can be written with this notation seen here. We are going to cover three methods for determining a limit: numerically, graphically, and analytically. Essentially, numerically is kind of the same as using a table, which is what we'll be focusing on in this lesson. So first we're going to look at the limit of a continuous polynomial, and we've just chosen a linear function, 2x plus 1, and we're being asked to determine the limit as x approaches 3 of 2x plus 1. So you're going to see different forms of this. So the numerical method, like I said, is kind of using a table approach. So what you should make note of is that there is a 3 here. That's the value that we're approaching from either side with our x values. And you can see that it gets closer and closer from the left and closer from the right. So we're approaching an x value of 3 from the left and right, and we're picking values that are very close. The fact that our first value is only a tenth away in either direction should give you an idea of how close we are. And then we just plug that x value into our function 2x plus 1 to get the corresponding y values. And what we're doing with these y values is observing if they are also approaching the same thing from the left and from the right. So let's see. From the left, we see 6.8, 6.98, 6.998. Seems as if from the left it's approaching a 7. If we look coming from the right, 7.2, 7.02, 7.002. This appears to also be approaching a value of 7. And when we look in the actual table of values, we can see the y value of the function when evaluated at 3 is also 7. So this means our left-hand limit, our right-hand limit, and the value of the function is all approaching 7, or is equal to 7. And this makes sense because, as it was stated, this is a continuous polynomial. So there's no holes, there's no jumps, no discontinuities to be worried about, and it makes it pretty clear that the output at 3 is 7, and the approach from the left and right match up with that. So that's how the table can be connected to the graph. And then there's the analytical method, the third method that we haven't really spent much time talking about yet, because this one typically takes a little bit more instruction and skill to build. However, because this is a continuous function, we can try to do direct substitution into this function. So f of 3 equals 2 times 3 plus 1, which equals 7, is the same thing we would get if we did direct substitution of 3 into this function. So as x approaches 3 from the left and right, f of x approaches 7. So that would be your final answer here that they asked you to observe. Okay, so let's take a look at another one. What about one that has some discontinuities? Because obviously this makes things more interesting. So the limit of a function with discontinuities, example 1. For the function f of x equals x squared minus 1 divided by x minus 1, find the limit as x approaches 1 of this function. And so for this, we're actually going to use a calculator to assist us. If you have your graphing calculator at home, you can use that. If you change your settings for your table to be in manual input versus auto input, and we'll go over this in class. However, if you have Desmos, you can just type in whatever x value you want, and that might be a faster approach for this particular example. Okay, so let's go ahead and do that. So I'm going to first try approaching from the left, and I'm going to plug in 0.9, which is right under, again, those values here are being determined by the fact that we're approaching a 1. So we'll start about a tenth away. So 0.9, I plug it in, and I get a 1.9. If I plug in 0.99, I get 1.99. I bet you can see where this is going. If I plug in 0.999, I get 1.999. Okay, and again, this is when I plug it into this expression, x squared minus 1 over x minus 1. Okay, so as we're approaching from the left, it seems like we're getting a value approaching 2. And you can also see this on the graph. As I approach from the left, it seems like, and I know it's very hard to see this, but there's a little tiny 6 here, because these are going by 2's. So it seems like we're approaching a 2. Now let's come from the other direction. So if I plug in a 1.1, I get a 2.1. I plug in a 1.01, I get, are you ready? 2.01. And if I plug in a 1.001, I get a 2.001. So as we approach from the right, it also appears to be approaching a y value of 2. So it seems as if this y value of our function should be a 2. However, if we plug in a value of 1 directly into that function, we would get 1 squared minus 1 over 1 minus 1. And unfortunately, that is what we call indeterminate form. And so your calculator is going to be very unhappy, and you're going to get an error. And if we take a closer look at this function itself, it kind of makes sense, right? We know that x squared minus 1 can be factored into x plus 1 times x minus 1. And we also can see from the graph that what's happening here is we're getting a whole. So essentially, the reason all these other values were very similar to what we were plugging in, just off by 1, is because this expression simplifies to x plus 1 once we remove the discontinuity that is occurring at x equals 1. So in this case, this is what, anytime you're looking at a table and it seems like the limits are matching, but the actual output at that value is not matching that, that means there has to be a whole. Okay? And this kind of summarizes what I just gave you a spiel on right here. So by direct substitution, you're going to get what's called indeterminate form. And you're going to hear that later in this unit and down the road. And it's important. Okay, so that 0 over 0 is a problem. But we would still say that the limit exists and that f of x approaches 2 as x approaches 1 from the left and right. So even though we can't evaluate the function, the limit as x approaches 1, our left and right hand, they match. And that limit is equal to 2. All right, example 2 of something with a discontinuity. So this is one way you might see a whole take form numerically. How else might this look? Well, maybe you're given a piecewise function, and we're asked for the limit as x approaches 3. Well, this one's pretty easy to figure out from just kind of looking at it what the table values will be, right? If I am approaching from the left and the right, I'm going to be using this because that's when x is not 3. So basically, I know in my table that these are going to be 2's, and these are going to be 2's because all of those values are not when x is 3. So clearly, what I'm approaching from the left is a 2, and what I'm approaching from the right is also a 2. However, what's actually happening at 2 is different, right? We're getting a different value. Okay? So even though the limit exists and is equal to 2, this actual evaluation of the function is happening at a different value. Okay? So those are the two ways you might see a whole in table form. Basically, that's when your left and right hand limits are lining up, but the actual evaluation of that value is not part of that. Okay, so what is it going to look like numerically when we have a limit that fails to exist? Case 1 is taking a look at when the left and right hand limits do not match. They don't approach the same value as x approaches a given c. And for this example, we're going to take a look at the limit as x approaches 0 of the absolute value of x divided by x. Now, it's very easy to pick up on this graphically. It's a very visual thing. You can see that this bridge is not forming at 0. And this is what you will later know as a jump discontinuity. So as we approach from the left, you can see one distinct value that the function's approaching, which in this case is -1. But then as we approach from the right, we're getting a very different value. They are not approaching the same thing. And even though -1 and 1 are not that far apart, they're definitely not the same. So in this case, when we have two different values from the left and the right, we can state that the limit does not exist. And it actually isn't even that important to us what the value is at the given c that we're approaching for the x values, because it could be that one of these are filled in even, right? So you might not even have an error here. We could easily have a -1 or a 1, and this limit would still not exist. So remember, when you're looking at limits, especially in table form, it's more about what it's approaching than the actual evaluation of that x value, okay? So this, in fact, is another indeterminate form when we do direct substitution of 0. Again, you're going to get very familiar with that phrase. But the important part is that f of x approaches different values, and that's how we can see that the limit doesn't exist in our numerical table form. So now let's look at case 2. The function is unbounded as x approaches c. Okay, so for this particular example, we're looking at the graph of 1 over x squared, and we're looking at 0 again, because 0 is a very common problem for a lot of functions. So again, from the graph, it's pretty clear to see that this is going up to infinity from the left and from the right, and so we are not approaching a finite value. The limit is not going to exist. But numerically, how are we going to be able to see this? Well, as we approach from the left, it seems like it's growing in a very quick rate, right? It's not growing in a very methodical way. It just seems somewhat exponential even. And so this one looks like it's getting very, very large in a positive direction. As we approach from the right, it's getting very, very large as well. And whenever you guys are doing these problems, it is fine, especially at this point in the unit, to continue putting does not exist, because technically that is true. There is no finite value. This function is approaching at 0. But do make a note that as we get further into this unit, and especially in the course, you're actually going to write infinity as your answer if it is actually approaching it from both sides. So for the sake of this video, yes, this is one way to know that it's not going to exist as a limit because it's unbounded, okay? However, also know that, as confusing as it may sound, you often are going to put infinity or sometimes negative infinity as an actual answer to a limit, just because it gives us a clearer picture of what's actually happening with that function at that x value. Now, if instead one of these had been going to negative infinity, then we would only be able to write does not exist at any point. Okay, the third case. Case 3 is the function oscillates. This is probably one of the more confusing ones in the numerical form because it's not as clear. And what you're looking for in this case is, kind of what's happening on the graph, right? So it's oscillating in that it's bouncing around. Okay, so as we approach from the left, it's going from 0.544 to 0.506. So that's going in a down motion. And then it's going down again into the negatives. And as we approach from the right, it's going from more negative to less negative. But it doesn't really seem like there's any type of pattern or uniform growth or decay here. But like I said, it's not super clear sometimes with these oscillating ones. In fact, these are going to be easier to spot if you're just familiar with the actual functions that create oscillating functions. They're going to be trig. They usually have really gross decimals. This one's a particularly example because usually it bounces from positive to negative, and that makes it very clear. This one's a little sneakier about it. But you can still tell that it's not going to approach the same thing from the left and right regardless. So even if you're not super sure it's oscillating, you can tell it's not going to approach a set value. And so in that case, we would still clearly be able to say that the limit does not exist. Okay? And I guess this is a better way to say it, that f of x oscillates faster and faster as x approaches 0. So that amount of change is going to get more and more extreme the closer to 0 that you get.